So hello everyone. Today I Kishan Kashyap is going to discuss about speed measurement using electromagnetic transducer. This is a part of the course PHN 310 that is applied instrumentation taken by the professor Mahengo. So in this experiment, let's start with the introduction. So this experiment showcases how electromagnetic induction can be used to measure the rotational speed of a shaft by placing an ferrous object with varying magnetic properties like toothed disc with slots near the electromagnetic transducers, that is near the electromagnetic pickup sensors. Usually these are the coil with permanent magnet inside it. Near the EM transducer, we aims to visualize how the changing magnetic field induces the voltages in the coil via Lenz's law. This voltage variation is then related to the speed of the rotational shaft. So the apparatus required in this experiment is, first we need a speed measurement trainer kit, which is shown in the figure. It consists of electronic circuit basically, with 1 Hz clock, a wave shaper inbuilt inside, a multiplier and a pulse counter. Apart from it, there are reset switch. This is basically used to reset the display whenever required. There is a push to toggle switch. Basically it is used to count pulses whenever required. Then there is a 4-digit 7-segment display counter, which is used to measure the RPM and number of pulses to measure the speed. Then there is a motor with slotted disc, whose diagram is in the next slide, an electromagnetic pickup near the disc, multimeter and digital storage oscilloscope. Here is the diagram of electromagnetic pickup sensor, MPU sensor. Here is the diagram of speed measurement trainer gate, where there is a knob to rotate the power supply, the external excitation source. Then the one of the ends goes to the sensors, where one of the end goes to wave shaper and multiplier and then counter. The shaft with 15 slotted disc is shown in the figure, and this is the digital storage oscilloscope which takes the digital readings. Now let's talk about the principles of electromagnetic pickup sensor. Basically, the electromagnetic pickup sensors operates on the principle of Faraday's law of electromagnetic induction, where the sensors detects the change in the magnetic field induced by the moving target. The sensor then generates an electric signals proportional to the speed of the target, providing accurate and real-time speed measurements. Now talking about the theoretical aspects, the EM transducers typically consist of a permanent magnet and a coil of wire wrapped around it. The permanent magnet creates a constant magnetic field that passes through the coil when the disc with slots or teeth is stationary. The magnetic field from the permanent magnet encounters minimal change as it passes through the coil. As the disc with teeth begins to rotate, the slots or the tooth basically disrupts the magnetic field from the permanent magnet as they come close to the transducer. This creates a changing magnetic field through the transducer, which basically, according to the Faraday's law of electromagnetic induction, a changing magnetic field passing through a conductor, basically the coil in this case, induces an electromagnetic force or voltage in the conductor. The magnitude of the induced voltage is proportional to the rate of change of the magnetic field. Faster the rotation of disc with teeth leads to a faster rate of change in the magnetic field, resulting in a higher induced voltage in the coil. The slot on the disc acts like an interrupter, causing the magnetic field and hence the induced voltage in the coil to vary periodically. The frequency of this variation is directly related to the proportional rotational speed of the disc. For instance, there are 15 teeth on the disc. For each complete rotation, the magnetic field will experience 15 disruption, that is 15 tooth passing by, inducing 15 voltage variation in the coil. Therefore, the frequency on the induced voltage is directly proportional to the rotational speed of the disc, multiplied by the number of tooth on the disc. While performing the experiment, when a magnetic material is brought near to the electromagnetic switch, it gives a very high logic at the output and gives low logic when there is no magnetic material near to it. When the motor gets applied, it rotates along with slotted circular disc. The electromagnetic switch has been fitted close to the slot of the disc. During rotation, when a tip passes through the electromagnetic switch, it gives a logic high signal and low logic signal when it immediately follows due to the air gap between the two slots. So in a complete rotation of disc, the sensor gives 15 pulses. In the signal conditional board, in the speed measurement trainer kit, these pulses are immediately passes through a wave shaping circuit to give them a perfect square wave shape. Then they are wave shaping circuit. Then they are multiplied by a multiplied circuit by a factor 4, basically 16 divided by 15, to show the speed directly in RPM. After multiplication, multiplying these signals are fed to a frequency counter that counts the pulses for 1 second and is then passed to the display unit. This There is a toggle switch for the display to show the speed in RPM and the number of counts. Two push button switches named as reset and push to count are associated for counting purposes. By counting the pulses for a particular second, we can calculate the speed manually. Now we toggle the toggle switch to speed. Basically, we then push the reset button 2 to 3 times until we get 0 reading on the display. Now we start the stopwatch, then push and hold the push to count button. We then stop the stopwatch after some second. Basically, say suppose we are stopping the stopwatch after 5 seconds. Then we release the push button switch and note down the count in the display. Then the rotation per minute is the value of rotation per minute is 4 into c by 4 into 5 by 4 into c by 5. Basically 5 is the t here, but what we supposed, according to the supposition, the t will vary. 1 RPM corresponds to 60 pulses per minute, which is equals to 1 pulse per second, that is 1 hertz. So basically RPM determines the frequency of multiplier wave. The formula is given for counting speed from speed counter and counting speed from, basically there is a correction here, counting speed from speed counter and counting speed from speed counter, RPM counter. In the first picture, there will be a counting speed from RPM counter. There is a slight mistake here. Basically, this is RPM counter. Sorry for the inconvenience. We'll see a video where we'll be demonstrating these things. So this is the presentation.
Hello everyone. So today we are going to study the performance of MQ sensors, that is electromagnetic pickup sensors, using speed measurement. So this is a multimeter. This is a digital cathode ray oscilloscope. This is a speed measurement ring. This is the readings. This is the MQ sensor.
So basically,
Hello everyone. So today we are going to study the performance of MQ sensors, that is electromagnetic.
This thing is the shaft with 15 slotted tooth. This is electromagnetic pickup sensor. When it comes close to the shaft, in the proximity to the shaft, it detects a higher signal, and when there is an air gap between the two tooths of the shaft, it detects the low signal.
Soft iron core. This is a ferromagnetic shaft.
This is a digital storage oscilloscope, and this is electromagnetic trainer kit, speed measurement trainer kit.
Through this we can control the speed and all, and this is the frequency AC response that is related. So what we do in this experiment is we first directly measure the speed from speed counter, and we check the differences. Like we again measure the speed that is measured by a sensor through RPM, and then we convert the RPM speed into normal speed, and we.
So basically what we do is we basically rotate the knob, which excites the excitation source, which increases the speed of the motor. We then measure the speed via pickup sensor, which the reading is passed to wave shaper, which reduces the unwanted noise, and which is then and converts the AC feeble AC signal into square wave signals, which is then passed to multiplier, which multiplies the incoming AC signal by a factor of 4, which is then passed through a counter, and the reading is then sent to the digital storage oscilloscope. So let's move to the next slide. So basically, this is the excitation source. We rotate the knob to increase the speed, increase the value that is coming here. This rotational power supply is then sent to the sensor. One is grounded, one is connected with shaft, and one is connected to the wave shaper. Now, this wave shaper, what it do is it reduces the unwanted signals coming from unwanted AC signals, which is sensed by the MPU sensors. Basically, MPU sensor, how it senses the uh, readings. Basically, when a ferrous material comes in very proximity to MPU sensor, there is a disruption in magnetic field lines. But when at this very next moment, when there is a air gap, there is no disruption in the magnetic moment. So these change in the magnetic field lines induces voltage in the coil that is wounded around that soft iron core, which inside MPU sensor, which that feeble induced voltages, induced AC voltages is then sent to this wave shaper, which removes the unwanted noise, which is then sent to multiplier, and which is then sent to counter. There is a toggle switch which is shifted between speed to RPM. RPM is the actual speed that is measured, and this speed comes from the speed counter, which is sensed by MPU sensor. This is push to count button, and this is a reset button. This will change the entire reading to 0, and this is actually a timer. Basically. So basically, here is the observation readings. This is a motor voltage readings. This is the frequency of wave shaper. This is the frequency of multiplier. These two comes after connecting it with digital storage oscilloscope. This is a counter reading. This is a reading taken while the toggle switch is shifted to the RPM mode. Now, to measure the speed from RPM, we multiply it by 85 pi by 60, basically 17 into time into pi upon 60, where 17.5, this factor 17 comes because of the diameter of the shaft. Now, basically, how we measure the speed from speed counter? Basically, we multiply it by 4. The, the readings, whatever the readings we get from speed counter, we multiply it by 4. We will know the calculation, and then we know the calculation from the from the last two, from the previous two slides. In automobile industries, basically automotive industry extensively uses electromagnetic pickup sensors for precise speed measurements in vehicle speedometers, transmission systems, and ABS systems. This technology basically ensures very high accurate speed readings, which contributes to the vehicle performance, vehicle safety, and compliance with regulatory standards. Some in-depth application being motion tracking and control, navigation and positioning, and safety and security systems like airbag deployment. All these involves the application of MPU sensor. Advantages of electromagnetic pickup sensors: very high accuracy, reliability, and non-contact of speed measurement. And solutions for that, like the challenges is that it faces challenges of interference of electromagnetic field lines and the calibration that is required to get the signal from that induced feeble signals. These are some challenges. However, the advanced signal processing unit that has been taken in the system has addressed these challenges, which ensures very optimal performances and accuracy in speed. The final conclusion of all these discussion on the today's topic is that electromagnetic pickup sensor technology offers very unparalleled precision and reliability in speed measurement, which benefits specific industries such as automotive, aerospace, and manufacturing industries. Its continuous evolution and integration with advanced technologies will drive further innovation and efficiency in speed measurement applications. Thank you. Thank you. If you have any questions, you can contact me by this